This code imports Python packages and modules required for data analysis, visualization, and creating a deep learning model with TensorFlow. Packages such as NumPy, Pandas, and Matplotlib are used for handling data, analyzing it, and creating visual representations of it. This code imports TensorFlow and its related modules to create and train neural network models. Sclearn is imported to measure model performance and preprocess data in this code.
Seaborn and Plotly are imported for more advanced data visualization techniques. This code is getting everything ready to analyze market data, create a deep learning model, and display the outcomes visually.
This code processes a time series data stored in a CSV file. It converts the date column into date-time format, sets it as the index of the data frame, removes the date column, and finally returns the modified data frame. In this specific case, the file named nebel_large.csv is being read and handled with this code. The term df is commonly used in programming to represent a data frame. A data frame is a data structure frequently utilized in libraries like Pandas and Python. It is a two-dimensional structure that organizes data in rows and columns, similar to a table or spreadsheet. In a programming environment that works with data frames using the command df, will show you the data stored in a specific data frame object that has been made. This allows you to see the contents of the data frame displayed in rows and columns.
Typing df lets you view the data in a data frame and check what's inside it.
This code creates a function named plot_data. The function plots line charts for each column in a data frame named df. Here is a straightforward explanation of the code's functionality. A copy of the input data frame df is made and named df_plot. The number of columns for the subplots is determined by the number of columns in a data frame called df_plot.
It determines the amount of rows needed by considering the number of columns and the desired number of columns per row.
A figure and axis for subplots are set up using PLT subplots. This code goes through each axis in the figure and creates a line graph for every column in the data frame using the !SNS line_plot function. This code segment defines how the tick marks, rotation angle, and major locator are set for the x-axis in every subplot. The figure's layout is adjusted using fig_tight_layout. Next, the plot is displayed using PLT show. There are a few problems in the code. The indentation of the last line, which is !PLT show plot_data df needs adjustment. The function is missing the return keyword in its definition. To make the code function properly, you must import the PLT and mdates modules. This code creates a function named filter_data. The function takes a data frame df and sorts it by the date column in ascending order. It then extracts specific columns volume high, low, open, close from the sorted data frame and creates a new data frame called data_filtered. It then displays the chosen features and returns the filtered data. If you're encountering an issue where the PD module in the code snippet isn't being imported, you can fix it by adding the following line at the beginning of the code.
Python import pandas as PD.
Python is a popular programming language known for its simplicity and readability. It is widely used for web development, data analysis, artificial intelligence, and many other applications.
Python's syntax is clean and easy to understand, making it a great language for beginners and experienced developers alike.
The code import pandas as PD is used in Python to import the pandas library and give it the alias PD. This allows us to access pandas functions and methods using the shorter alias PD in our code. This function is intended to filter a dataset named df. In this code line, a data frame named train_df is created by sorting another data frame named df by a specific column date. The copy method is used to create a new copy of the sorted data frame instead of altering the original data frame.
These are the features: volume, high, low, open, close.
This line of code is a Python command that will print or display the text feature list on the screen.
This code will output all the elements in the list named features.
In this code, a pandas data frame named data is created using the data from an existing data frame named train_df. This code is filtering the dataset data by selecting only the columns specified in the variable features.
This statement simply means that the filtered data is being returned.
A data frame object in pandas is created with a dictionary containing a column labeled date and two date values, the 1st of January 2022 and the 2nd of January 2022. This represents a volume range of 100 to 200.
The data range for high is from 50 to 55.
The range of numbers low falls between 45 and 48.
The range of values for the variable open is between 48 and 52. This code snippet specifies a dictionary named close with two key value pairs.
The key is close, and the corresponding values are 49 and 53.
The function "filter_data" filters the data in the data frame "df" and stores the filtered data in a variable called "data_filtered".
This term refers to data that has undergone a process where certain elements or information have been selected or removed based on specific criteria. This code snippet generates a data frame called df.
It then applies the filter_data function to that data frame.
The function keeps only the columns volume high, low opened and close. Finally, the data is sorted based on the dates column, and the filtered results are printed out. This function splits a data frame into training and testing sets, using a 70:30 ratio. It takes the data frame as input and calculates the split index to divide the data accordingly. The train_test_split function divides a data frame into two sets, a training set train_df from the beginning of the dataset up to a specified split index, and a testing set test_df plus a specific sequence length to the end of the dataset.
In the end, the function provides three outputs: the training set, the testing set, and the split index.
This code divides a dataset called data_, filtered into two sets, one for training a model train_data, and the other for testing it_data, test_data.
It uses the split function to randomly split the dataset based on a specified split ratio.
In this scenario, the code is dividing the dataset into training and testing components using a standard split ratio.
The testing dataset, known as test_data, is then displayed.
This dataset is crucial for assessing the model's effectiveness following its training on the training dataset. The code creates a function called preprocess_data that processes a dataset. It reshapes the dataset and scales it using min-max scaler to ensure it falls within a specific range.
The function outputs the scaled data and the corresponding scaler.
The code performs a pre-processing step on two datasets, a training dataset and a test dataset, using the preprocess_data function. After the process, the scaled datasets and their respective scalars are saved in separate variables, train_data_, scaled with the scalar for training data, and test_data_, scaled with the scalar for test data.
This code separates a dataset into two parts, the input data X and the target data Y, to prepare it for use in a machine learning model. The code requires as input the length of the sequence and the original dataset. Starting from the sequence length, consider each row in the original data.
An input sequence X is created, which includes a specified number of rows before the current row called sequence_length. A target value Y is generated to represent the next row following the input sequence. In the end, it transforms the X and Y lists into NumPy arrays and then sends them back. This code is intended to format the dataset before using it to train a machine learning model. A variable named sequence_length is assigned the value of 100.
The program partitions the training and testing data into sequences of length 100, using a function called partition_dataset.
This function will separate the data into input sequences for training, X_train, output values for training, Y_train, input sequences for testing, and output values for testing, and output values for testing.
It displays the dimensions of the training input X_train and output Y_train datasets.
This code displays the dimensions of the test input X_test and output Y_test datasets.
The code outputs the first value in the training dataset, which is stored in the variable Y_train zeroed.
This code snippet is displaying the value of a particular element in two separate arrays. The first line shows the element in the array X_train at index 1, and a position specified as sequence_length 1. The second line displays the element in the array Y_train at index 0. This code uses LSTM layers to build a sequential model for a machine learning task. The variable out is assigned the value that represents the number of columns present in the _test dataset. The model begins as a sequential model. The model has two long short-term memory layers with configurations such as the number of units, 128 and 64, input shape, return sequences, and ReLU activation function.
To prevent overfitting, dropout layers with a rate of 0.2 are included after each LSTM layer.
This helps enhance the model's generalization by randomly dropping out a proportion of connections during training. A dense layer is added with the number of neurons equal to the value of out. The code sets up an optimizer called Atom with a learning rate of 0.001 and compiles the model by using mean squared error as the loss function. This code creates a neural network model with LSTM layers for predicting sequences or forecasting time series data. The model is trained using the Atom optimizer and mean squared error loss.
This code snippet performs the following actions. Early stopping is a technique used during model training that stops the process if the validation loss does not improve for 5 consecutive iterations. This process involves training a neural network model using the provided training data for up to 100 training cycles epochs.
A batch size of 32 instances is used during each cycle, and the model's performance is evaluated using the validation data. An early stopping callback is utilized to halt the training process if the model's performance on the validation data does not show improvement. Once the training process concludes, the model that has been trained is saved to a file called my_model h5 within the model directory. This file includes the model itself as well as its optimizer settings.
This allows for the model to be easily retrieved and utilized for future purposes or deployment.
This code generates a visualization that displays the training loss and validation loss of a machine learning model across different training epochs. When using PLT figure A fig size equals 25, a new figure is generated with a specific size of 20 units in width and 5 units in height. When using PLT subplot 1, 2, 2, the plot is divided into a grid with 1 row and 2 columns. The second subplot is then selected for plotting. This code _PLT plot history loss label equals training loss is used to graph the training loss values that are saved in the history object. Using PLT plot with history val_loss will show a line plot of the validation loss values recorded in the history object. The code _PLT legend lock equals upper right places a legend on a plot at the upper right corner.
This code PLT x label equals 16 sets the x-axis label ep with a success label as epoch with a font size of 16.
This line of code PLT y label loss font size equals 16 is used to set the label for the y-axis of a plot as loss. The parameter font size equals 16 sets the font size of the label to 16. This code line sets the y-axis limits on a plot to start at 0 and end at the maximum loss value. The line PLT titled Training and Validation Loss font size equals 16 is used to set the title of the plot and adjust its font size to 16. To show the plot, use PLT show. This code creates a graph that shows how the loss of a machine learning model evolves across various training cycles for both the training and validation data. It helps to assess the learning progress of the model and to detect signs of overfitting or underfitting. This code uses a machine learning model named model to predict outcomes based on data stored in the variable x_test.
The predictions are saved in a new variable named test_predict. This code snippet performs the following steps.
The process begins by undoing the scaling transformation applied to the test_predict array, resulting in the retrieval of the original unscaled values and then storing them back in the test_predict array. Afterwards, the scaling transformation applied to the y_test array is reversed, and the original unscaled values are saved in the y_test_scaled array. When the process is complete, it then shows the shape of the test_predict array after it has been transformed without scaling.
This code computes various error metrics to assess how well a machine learning model is performing.
RMSE, which stands for root mean square error, is a way to determine how close predicted values are to actual values in a model. The lower the RMSE, the better the model's performance. The mean absolute error (MAE) calculates the average difference between predicted and actual values without considering the direction of the errors. It is a more robust measure compared to root mean squared error (RMSE) when dealing with outlier values.
MAPE, which stands for mean absolute percentage error, is a formula used to determine the average percentage difference between predicted and actual values.
This metric offers valuable information about the size of errors compared to the actual values.
MDAPE, or median absolute percentage error, is a metric similar to MAPE, mean absolute percentage error, but it calculates the error using the median instead of the mean. This makes it less sensitive to outliers in the data and offers a different way to assess the accuracy of a model.
Each metric is computed for a designated column, ith, in the test data and is subsequently rounded to 2 decimal places before it is shown. In this code snippet, there is a data frame named df that is divided into 2 parts, train and valid. The split is determined by a variable set within the code. Train holds the data from the beginning of the original data frame up to the split point, while valid holds the data from the split point to the end of the data frame. Next, a new column called predictions is created in the valid data frame. This column likely contains predictions made by a model taken from the 4th column of the test_predict array. Once the process is complete, the program will display the updated valid data frame. This data frame will include the original data as well as the predicted values in the predictions column. This code displays a graph showing data related to the stock market. The plot figure size is set to 16 by 8 inches. Afterwards, a title is included on the plot named Model, with the x-axis labeled as Date, and the y-axis as Close.
It shows the closing prices from the training data on the graph. The program displays the close values of the validation data on the graph, along with other data.
It then displays the predicted close values as a graph alongside the actual data. A legend is included in the plot to distinguish the lines that show the training data, validation data, and predictions. To show the plot, we use PLT show. This code creates a visualization that compares actual and predicted closing prices of a stock on a test dataset. The plot displays 2 lines, one for actual closing prices and the other for predicted closing prices, with dates on the x-axis and closing prices on the y-axis. The plot is titled Actual versus Predicted on Test Data and has a figure size of 16 units in width and 8 units in height.
This code reads data from a CSV file called nebule_large.csv in a folder named data.
It saves this data in a variable called new_df, and then shows the content of new_df. This code generates a plot using data from a data frame named new_df, and then shows the plot using PLT show. The PLT show function displays the created plot for the user to see on the screen. This code is designed to filter a data frame named new_df by passing it to the function filter_data. The function applies certain filtering criteria to the data in new_df, resulting in a new data frame that contains the filtered data. The filtered data frame is saved in a variable called new_data_filtered and is shown in the output. In summary, this code is useful for isolating specific data from new_df for future analysis. This code prepares a dataset called new_data_, filtered by pre-processing it. The pre-processed data is then presented as new_data_, scaled, along with the pre-processing tool scaler used.
The pre-processing steps involve adjusting numerical features, dealing with missing values, converting categorical variables, and other required data organization steps. The scaler is beneficial for future use in applying the same processing steps to new datasets as the original one.
In this code, the variable sequence_length is assigned the value 100. The function partition_dataset is then executed with sequence_length and new_data_ scaled as inputs, and the results are stored in variables x and y. Lastly, the code displays the shape of the X array. This code separates a dataset called new_data_, scaled into two parts, labeled as x and y, with each part containing 100 elements. It then shows the shape of the X array to demonstrate the size of the divided data.
This code retrieves specific elements from the lists X and Y.
The first line prints the second sublist of list X at the position defined by sequence_length 1. The second line prints the element at the first position of list Y. This code is getting the size of a scaled dataset called new_data_ scaled, and then fetching the element at an index determined by the negative value of a variable called sequence_length. The dataset size indicates the number of data points it contains, and using a negative index helps access a particular point from the dataset's end. This code is organizing the input data to match the required format for a machine learning model. The variable n_steps is assigned the value equal to the length of a sequence. To create x_input, you take the last n_steps, rows of a dataset called new_data_ scaled, and include all columns in those rows. To reshape x_input, change its dimensions to 1 n_steps, number of features in the data. This code selects the last rows of the data and rearranges it to match the needed format for a machine learning model. This format is important for the model to be trained effectively.
This code is like a magic crystal ball that makes predictions about what will happen next by using a special formula. First, it creates an empty list called lst_output. Then it sets the forecast horizon to 30 time steps. It iterates through each time step in the forecast horizon.
A machine learning model is used to forecast the next value by analyzing the input data x_input and adding this prediction to the lst_output. It adjusts the prediction to have the same shape as the input data. The input data x_input is updated by removing the first element and adding the predicted value at the end. This method allows the model to use its previous predictions as input for the next prediction. This code goes through 30 time steps, predicting outcomes at each step.
It updates input data for the next prediction by using the previously predicted values. This code snippet reverses the normalization or scaling applied to a list of output predictions, lst_output.
By using the inverse_transform method of a scalar object, it transforms the predictions back to their original scale. It then isolates the last column of the transformed output, marked as -1, and saves it as lst_output_close. Ultimately, it outputs lst_output_close, which holds the predictions converted back to their original scale. This code snippet filters the closed column from an existing dataset called new_data_filtered and stores this filtered data in a new dataset named dataset. The new dataset only retains the closed column from the original dataset. This code does the following. A data frame is made using a list of outputs named lst_output_close. The column in the data frame is labeled as close and named forecasted_values. This function determines the size of the original dataset.
A new date range is established for forecasting values by setting it from the last date of the original dataset to a defined forecast period.
The function sets the index for the forecasted values data frame to a new date range. It displays the data frame with the forecasted values.
This process involves combining the original dataset with the forecasted values data frame by stacking them together in rows.
A plot is made to show the original close prices alongside the predicted close prices. The plot displays the initial closing prices in blue, alongside the predicted closing prices in orange, with all necessary labels included for clear understanding. This code creates predicted future values for closing prices, adds them to the existing data, and displays a graph to show how the predicted values compare to the actual closing prices.